Thanks for the invitation, Roya. I am required to use the mic, as the nice gentleman back there told me, and I'm not allowed to move around too much. So I'll be here. Like Roya mentioned, I work on a lot of stuff, which some of my grad students have said is sometimes very confusing. They go away for 2 weeks and they come back and there's like a whole new topic. So I do work on different materials, and to me, soft materials were new materials. I had never worked with them before. I don't really work with soft materials in the sense that I mostly use them to my advantage. So I'll talk about some work we did with nano-assembled adaptive structures. These are some of the highlights of some of the work we've done, and I won't talk about all of them, just a few. And I'll tell you briefly about what the commonality is amongst them. So to start with, we start here in nanomaterials. So small is different. We all know that what bulk gold looks like, many of us. If we look at 12 nanometer gold particles, then they look red. So this is an ancient difference, this variation with size and color was observed a long time ago. This is not, gold actually can be more versatile than this. This is a very simple plot of gold solutions of different sizes, and you can see that the color tunes over a fairly large range. This property of gold was first used in the Lycurgus cup, which is in the British Museum. The cup is set up so that there is a light source inside. You can first view it as is. It appears green. I'm sorry, spaz. And if you turn the light source on, it appears red. So observed in reflected and transmitted light, it's a different color. And what this cup consists of in the wall are ground particles of silver and gold, which was known then to impart interesting optical properties. The older stained glass windows of churches are also ground metallic particles. They're not actually paint. And so they don't bleach with time. They always appear bright, and you can see the color in transmission. So metallic particles have a lot of interesting properties. Nowadays, of course, we don't have to grind up metal. We can grow them in many different types of shapes. The rods, cubes, triangles, more complicated shapes, and even more. These are sometimes called nanostars and sometimes called nano-urchins. Based on the morphology and the size, this color changes. There's part of the spectrum where they absorb most strongly or where they reflect strongly, of course, tunes. And all of these have different resonances in the visible spectrum and different strengths of resonances and so on. So these are metallic nanoparticles. The interesting particles of nanomaterials, interesting properties, are not just confined to metals. Semiconductors are another example where changing the size, quantum confinement, can give it a lot of different properties. This one is an example of where we moved on from just simple nanomaterials to trying to assemble them in specific geometries. These are called super-lattices. Normal lattices are made up of atoms. When we make lattices out of artificially made atoms, we call them super-lattices. That's mainly because we tend to name things we have made ourselves as superior to what occurs in nature. This one here is made from two different types of semiconducting nanoparticles called quantum dots. Cadmium telluride has a slightly bigger diameter, cad selenide a slightly smaller one. The difference between these two here is the ratio of the two types of quantum dots. They are mixed in different ratios. They are deposited on substrates and allowed to anneal, and they arrange themselves in different geometries just arising from how many of each kind are present. And this particular paper, it was one of the first demonstrations where artificial matter or superlattices were formed on a large scale using nanomaterials as the building blocks. And they had interesting optical properties. The optical properties were a superposition of the two kind, and they could be tuned somewhat by varying this, the proportion of each type between them. So that then brought us to the next question is where if we want to make new materials with different functionalities other than what are currently available in nature, do they have to be crystalline? Do you need long-range order for functionality? How important is that? And in that regard, here are some examples where we have demonstrated since then that for a material to function well, it does not need to be a crystal, or it does not need to have a very perfect long-range structural order. This is an example of amorphous diamond. Interestingly, amorphous diamond is actually harder than the crystalline diamonds that we all love to wear because it lacks the crystalline planes. So diamond can be cleaved along some planes. This one does not have that structure. So it's actually harder. So if you are considering diamond for its hardness, the material property, then amorphous one is just as good, if not better. Here is an example of a superconductor, a molybdenum silicon. It's an alloy. The crystalline material has a Tc here. The amorphous material actually has a higher transition temperature. So it can go superconducting at a higher temperature. So that's considered an improvement. You might or might not have heard of amorphous silicon in solar cells. They allow flexibility in the way that crystalline silicon panels often don't. And more importantly, crystalline silicon panels have to have perfect crystalline structure. So you have to spend a lot of effort, invest considerable funds in their growth. Amorphous silicon cells, because they're amorphous in the first place, they can absorb a lot of defects and still function well. So that's another advantage. And this is one of my favorite amorphous matters. It's a ferrofluid, a very strong magnet, which is not a crystal, mostly fluid-like. So then we come to this conclusion that for a material to function in a specific way, it does not have to be a crystal. It does, though, need to have some properties. On a macroscopic scale, it has to have some sort of uniform or predictable interparticle interactions. And there has to be some sort of short-range order. It cannot be absolutely disordered. Amorphous materials do have short-range correlations. With that, we decided that we would like to take this approach, use or sort of make amorphous materials, mix them together, forget about having long-range crystalline order, and then perhaps then we can make them into new functional materials. Before I go into our efforts of where we started making new materials by assembling nanoparticles, I just want to talk about what I mean by adaptive structures. This is a word that is very commonly used. In my head, when I say adaptive structures, this is what I'm thinking. Something that has a collection of building blocks. You can use them as you wish to build whatever you need. This particular Lego set can let you build either of these three, depending on, at that time, whatever you feel like. So then these are adaptive structures. They can adapt one to the other. The thing becomes, how do you make it change the shape? If it's in the shape of a boat here and you want a plane, you have to then go in and get someone to do it for you. It won't change. There has to be an agent of change. So what we want then is to assemble nanomaterials and then assemble them in a way that you can change the properties on demand. An adaptive responsive material that can respond to stimuli and change its structure and its functionality without us having to go in and do it ourselves. So with that in mind, we decided we would choose a responsive matrix. And for that purpose, we chose liquid crystalline materials. This is, in short, my foray into soft materials. Liquid crystals are in between liquids and solids, as the name suggests. If this is a crystalline solid that has perfect positional and orientational order, and this is a fluid or a liquid that has neither, a liquid crystal falls in between. It has some sort of orientational order, some kind of positional order, but not really long range. In case of liquid crystals, by changing the temperature, we can change the extent of ordering, and we can actually visibly see the color change because the color is a reflection of how ordered this system is. And this particular color property has been demonstrated and used in lots of little everyday objects. The sort of things we buy called mood rings. They are just thermotropic liquid crystal. They can be used for temperature sensing on a strip. It can sense the temperature, and the color will reflect that. Apart from temperature, another property of liquid crystals that we are all aware of is how they can be controlled by electric field. So this is 2 electrodes here, liquid crystal molecules, no electric field applied. We apply a field, the liquid crystal molecules line up in the direction of the field. This is known as Friedrich's transition, and we have all sort of seen this in our liquid crystal displays. This is what all of us are still using. We have a sort of a display system like this. We have a screen here. The molecules are entirely randomly ordered. When we apply a voltage, they line up and they allow light to be transmitted through. We have a pixel that appears bright and a pixel that appears dark. So liquid crystals then allow changing of the property with temperature and with field. Our idea is that if we had nanoparticles in here, changing the host matrix would allow us to change the nanomaterials properties, and we'll see how well that works out. Just a little bit of liquid crystal stuff before I go in further, because we look at images mostly, and so I just want to establish what the images will mean. In a liquid crystal arrangement, we have, this is what we call the nematic phase, the phase which has some average orientational order designated by this arrow, which we call the director axis. And this is what we call the isotropic or the fluid disordered phase, where there is absolutely no order. Here, it's just a liquid. And the angle between the director axis and the orientation of any particular molecule here is shown here, and this average value gives us a measure of the order parameter. When we are looking at liquid crystalline materials, here's how we view them. We put them under a microscope with crossed polarizers. So we have 2 polarizers that are crossed. The liquid crystal material is in here. This is the angle between one of the red polarizer axes and the director axis, N. So here, this director axis is oriented this way. So the ordering is such that N is oriented like that, and the image appears bright. So what's happening is the light that's going through the first one, half of it makes it through the liquid crystal, another half makes it through the bottom one, and we get some light out. When we rotate the sample between the polarizers, the intensity changes till it becomes black when this N orients with any one of the cross polarizers. So you can think of the liquid crystal nematic material acting like another linear polarizer. And that's how you can tell. If this liquid crystal here was like that, it would appear black all the time. It would not change with change of angle. So that's our test. That's how we know we have a nice phase or not, we have order or not. Okay, so now that we've established the part of liquid crystal that we care about in this talk, we start putting nanoparticles in there. First, we put a single nanoparticle. Here's the nanoparticle here. You can see a little bit of fuzziness around that. These molecules are called ligands. All nanomaterials need them, otherwise they will just clump together and not be so nano. In the liquid phase, the sort of the fluid phase, the liquid crystal molecules are all arranged anyhow. No one cares, everybody's happy. When we cool down and these molecules are trying to orient in some particular direction, these ones can't. They are still sort of they're interacting with the ligand molecules. This is called a hedgehog defect. And every defect causes energy. So the liquid crystal is really unhappy when we put nanoparticles in there when it's in this nematic phase. So if we put a whole bunch of them and we cool down, instead of each of them forming tiny hedgehog defects everywhere, the liquid crystal pushes the nanoparticles into these regions so that they can be fewer, larger defects, but fewer. So fewer is better. That's a lower energy cost. So that's when we then put nanoparticles in here and cool it down. The nanoparticles, our first experiment we did were with quantum dots, are expelled from the ordered phase into the disordered phase. And this is what the experiment data from which looks like. This work was done by Andrea Rodati. That's her picture there. We put the liquid crystal, you're looking at the fluorescence from a quantum dots in liquid crystal molecule. 40 degrees, the liquid crystal is isotropic, so it looks black. We are cooling down. The liquid crystal is starting to get organized, so it's expelling all the quantum dots into these defect parts till we come in. The phase has come in all the way, and all the quantum dots are packed together into defect regions. The rest of the liquid crystal is perfectly ordered. So we can have the liquid crystal bring about some sort of self-assembly of the quantum dots when we started out with a completely dispersed system. Then we look at the clusters, like what do the clusters look like? If after all of this, what we've created is this giant pile of quantum dots with absolutely no order, then it's no good. We kind of ended up worse than we started. We did some small angle X-ray scattering. What we are looking at here is just the liquid crystal with no quantum dots. This is quantum dot in liquid crystal, and we see a very nice peak here. We convert that to distance, and we find the distance on average is 7.6 nanometers, which measures to be exactly the center-to-center distance when the quantum dots are closely packed together. Also, interestingly, the width tells us that there isn't a huge spread of this distance. It's not like we have some of them 100 nanometers apart and some 7. They're all close by. So when we sort of came up with a cartoon that represents what the quantum dots might look like in the cluster, they don't form a lattice, obviously, but they do form some sort of an amorphous network like this, where they are in clumps, but within the clumps, they are almost equally spaced from each other. So that's kind of nice, because we do want some sort of short-range order. So, and these clusters are large. They're almost microns. So it's on a microscopic scale. So we're kind of getting to those amorphous states that we wanted to in the first place. But still, let's look at what these clusters actually look like on the optical scale. So we take a small region. We do some scanning PL microscopy here. We are plotting the wavelength of emission of the dots. We look a little bit closer, and here's what we find. So in quantum dots, the color is a measure of the interparticle interaction. The redder the color, the more it's a measure of how the quantum dots are exchanging information. If it's very red, or if there is a big gradient, that means there is a big variation. If it's very uniform, and we took some line cuts here, you can see the color is very uniform inside a cluster. That means that the cartoon that we have of the quantum dots sitting at almost equal distances throughout this big giant cluster is good. So although the liquid crystal is assembling them into aggregates, it's not true aggregation. There is some sort of short-range order in the aggregates. So we've organized them in a nice layer, if you want, in 3 dimensions, of course, but there is some sort of ordering in the system. So after this experiment, we decided we would then, we made clusters with one kind. The next step is you make clusters of 2 kinds. So you put 2 things together. This effort was led by UC, who's here. Both Andrea and UC have since graduated. We put quantum dots and magnetic nanoparticles in the liquid crystal, did the same procedure, cooled them down, made them form clusters. We did X-ray scattering to make sure that the particles were actually in the same cluster. And then we put them in our cryostats. We are imaging the emission intensity of these clusters. The magnetic nanoparticles don't emit any light. The quantum dots do. So we're looking at the emission from the quantum dots. And as we apply a very small field, the emission intensity from the quantum dots increase several-fold. So we have a mixture of quantum dots and nanoparticles. We apply magnetic field, the quantum dots start emitting brighter, which was a weird, unexpected observation. The other thing we looked at here, we are plotting the wavelength, the color that it's emitting. We also find that with the application of field, the clusters get squished. So we are plotting the cross-section of the clusters, the spatial cross-section. With the application of field, they are always narrower. So somehow, when we apply the field, the liquid crystal is reorienting in a way that is squishing the clusters closer. We can actually calculate the compression factor of the clusters as a function of field through this imaging. And also, this effect is reversible. When we turn the field off, the whole arrangement relaxes, and this brightening goes away. It's a little bit hysteretic. It's here. After all, it's a spatial arrangement on this scale. It's not going to be exact. When we remove the field, the effect goes away. So what we came up with here is you can use this as an optical sensor for magnetic fields. So for example, you stick one of these, say, on your arm. I'm not sure how. Maybe it's on your watch. You enter a region. If you are sensitive to fields, that thing will emit brighter, and you know that you're entering a region with stray magnetic fields. And you can save your laptops and your credit cards from being destroyed later on. So it's just a little example of what you can do when you put these sort of hybrid materials together. But after this one, we thought that it's all nice to form clusters, but we need to make something that is a little bit more ordered than clusters. So we decided to talk to chemists. Sometimes you have to do things in life as an adult you never thought you would. So you meet up with chemists, and you tell them how you know no chemistry whatsoever, but could they please help you out? So what the chemist people said was, well, these molecules, you don't have to always be stuck with them. We can exchange them out into any other molecule you want, which was like amazing to me. So I said, sure. In that case, let's put molecules on them instead that look like the liquid crystals themselves. Because this is what happens when we put in liquid crystal and the nanoparticle with these linear ligands like that. They form the defects. But if the ligands have this sort of green areas that look like the liquid crystals, then maybe it'll organize like this. And maybe the defects won't form. And then, I don't know what else will happen, but it could be different. It should be nice. So the chemist faculty, they looked at what the liquid crystal looks like. Here's the liquid crystal molecular structure. This is this liquid, the benzene ring area. This is just a long carbon chain. This one, these two form this rigid region that we represent by this sort of blue part here. So they said, we'll make a ligand that looks like this. This side attaches to the nanoparticle here. This one is this green area, another rigid part that will look like your liquid crystal over here. So we said, OK. They showed us how they make them. We tried. That didn't work out. They make the ligands. We do the ligand exchange on the nanoparticles. And then we follow the same procedure. We put them in. We sonicate them for like hours, put them on a hot plate, cool it down, the same procedure we did that gave us aggregates. And this work was done by Makiko. And here's what we see. So we have nanoparticles in liquid crystal, and we are cooling it down. And this is in real time. We are cooling it down. They are expelling them into these regions like always. But instead of forming the aggregates, here, the new ligands start linking with each other, and they form these shells. So, and that's where the process stops. So we have shell formation. We do SEM imaging. The first time you see this on images, you can't believe that you formed shells. Here's an entire shell. We managed to get some broken ones, and you can see that they're actually hollow. So this is the shell wall. It looks like a little hollow bowl. We did a close-up of the shell wall. These are with an SEM, not a TEM, so they look fuzzy, but we are really pushing the SEM to its limit. These are the nanoparticles in the wall. They are almost close-packed, not entirely. There's some disorder, obviously, but they are pretty nicely packed in the wall. So they form the wall here. This is entirely made out of nanoparticles, nothing inside, and the nanoparticles stick in some sense because of the ligands that we put on them. So since we could form these shells, the next thing we thought is maybe we can put stuff in them. When you see something hollow, your first instinct is to stuff it with something. That's how we came up with Thanksgiving. So we put red dye inside the shells. How do we put the dye? We just mix it with the liquid crystal, and it grows, and it encapsulates the dye within. We monitored the intensity of the dye over a long period of time, because now we are putting things in a shell whose wall is not actually solid. It's made out of nanoparticles, closely packed, but still it's like a porous shell. Chances are this thing would leak out, but it actually, if you look at the intensity, there's very little change. It encapsulates the dye really well. And we looked at the dye intensity for about 5 months, and there's very little loss of the total dye inside. We even we did some control measurements that said the decrease in intensity could actually be not leakage, but dyes just bleach with time. Their emission intensity goes down with time, so that it could even be partly that. So this shell with a non-solid wall can encapsulate dyes. We tried this with cancer drug Taxol for 5 months, longer than most systems can encapsulate a foreign object. After you put things in it, the fact that it can hold, then comes the question of how do we release this dye or the contents when we want it to. So the first thing is we heat up the shells. We are heating the shell here around 108 degrees Celsius. And this is heating just by putting it on a hot plate. And you're looking at the fluorescence of the dye inside. That's why we can see them. These shells are made out of gold nanoparticles, so they don't emit any light. It's starting to get fuzzy, which means the dye is starting to leak out. Within about 6 seconds at the same temperature, all the dye comes out. Presumably, the shell has broken. And the reason why the shell breaks at those temperatures, we can understand that when we look at the behavior of this molecule, the ligand that we put on the gold nanoparticle, the one that is causing the shell formation, it has one transition here around 80-something odd degrees, another one over here, slightly above around 130 degrees Celsius. So somehow in between the two, there is a small bump over here, and somewhere here is where the ligands are weakening. The interaction that was holding the wall together weakens, and that's why the shell breaks at that temperature. So we can form a shell, we can break it, but breaking with temperature is never as pretty. I mean, everything breaks with temperature at some point. So we thought if we could use something else to mimic temperature, it would make it cooler. So we thought of using light. So here we have a shell, and we're shining light on it, and it pops. And that's the shell is entirely gone. And this whole process takes this is also in real time. It literally took a couple of seconds. So we had the shell, we shine light, and we can break it with light instead of temperature. The two are kind of the same thing, but we'll come to that in a second. The reason why, in the previous case, we showed the color as green is because this property is called the photothermal effect. This is the absorption spectrum of the gold nanoparticles that make up the shell wall. This is green light here. This is where it absorbs most strongly. That is where the shell breaking happens. We did this as a function of wavelength. We can break the shell with light, slightly bluer, slightly red, but at light of this wavelength, the shell does not react at all, as long as it's being held at room temperature. These are frames of the same images. Here's the shell. Notice the shell is the one in the middle, not this circle. We'll come to what that circle is in a second. And here's the shell. In about 5 seconds or so, the shell breaks. The shell had dye inside, and the dye is released also as it starts disintegrating here, and it breaks over here. Just some numbers. This is very fast compared to most other platforms that use encapsulation and release. This is on the order of a few seconds. Typically, people need very high power over tens of seconds, and the highest power we've used is about 2 milliwatts. So it happens very fast at very low power. What happens? Why does it break? As I said, it's the photothermal effect, a property of all metallic nanoparticles. When we shine light of the right color, where they absorb strongly, the strong absorption causes the electron gas to oscillate. It rapidly, the sort of rapid heating here causes excitation, which the electrons then relax. And as they relax, the heat is going to go out to the lattice. There is nowhere else to go. And the nanoparticles don't have a lot of volume, so all the heat is dissipated in the surrounding medium. So it absorbs light, heats up, releases the heat to whatever is surrounding it. This effect has been used quite successfully in some cases. This is a mouse. You can see a tiny little tumor. It kind of freaks out physicists. I know, I'm sorry, but biologists love looking at stuff like this. Here's a mouse with a little tumor. Gold nanoparticles were injected at the tumor site and then irradiated with green light that it resonates with. And this is the remission after 10 days of treatment. So it literally just kills off the cells by heating them. Not an elegant way, but it's killing cancer cells. So that's in a mouse. If you don't like biological examples, here is one. What we are looking at is gold nanoparticle in water. And here you can see a bubble of steam forming. It can actually boil water. It heats up so much by just shining light. And this work was done, not this particular one, but work like this was done by Naomi Hallis. It was really nice. She has found this way that you can use this as a method to sterilize equipment when you're out in the field. If you're in Africa and you need to do surgery and you have no source of fuel anywhere, you take your nanoparticles, you can boil water and sterilize things if you like. The photothermal effect is very strong. So that's what's happening here. And finally, as part of the physics talks, I get to talk about some equations. This is the shell here. In about 1 second, this was the shell, and we saw this thing forming. This is the bubble that forms because this gold shell here is heating the medium, the liquid crystal around here. So the liquid crystal was in the nematic phase. The heat makes this part here become isotropic. When we look at it under cross polarizers, we can see that. This region appears black, while the rest of it remains ordered. So it's creating this phase boundary by heating. That's what that outer ring was. And we can use that to actually calculate how much heat we are producing near here. Because ultimately, if we want to put that near cells, you want to know how much heat that's going to produce, how many cells it will kill, how far. So this is a simple diffusion equation. We set up the temperature at any point R is given here. This is the heat we are putting in using our light. The thermal permeability, R is the position there. Okay, the other thing then, the equilibrium radius, the one that forms here before it breaks, at this radius, we know what the temperature is here. That's the transition temperature between isotropic and nematic. So we can rework this one to form this, and we can measure the equilibrium radius. We do that for different power, different wavelengths all the time. So this is the equilibrium radius. That is experimental. We can also rework this to come up with this equation here, where we plot R and we incorporate the equilibrium distance here, the radius that we can measure in here, where alpha is just this ratio of physical parameters of the liquid crystal. This is density, this is specific heat. And we can measure with the high-speed camera, we measure as this bubble expands. So we are plotting the bubble radius. You see the time is less than, this thing forms within milliseconds. So we use a high-speed camera there. We are plotting R as a function of 1 over t. Fit a straight line. The slope can give us alpha. So this sounds like a strange thing to do, but here's why we do it. We can calculate alpha. These are properties of the liquid crystal that's available in literature. We can get alpha from the slope here. Why we do this is first to establish this agreement. What that agreement means, this one in this equation, it looks like temperature is what we are looking for, but Q is also an unknown. You're shining a laser on a solution with a whole bunch of shells in it. You have no idea how much heat is actually, or how much of this light energy is actually being absorbed by one shell. We can at best guess. We guess, do some calculations here. We need another independent way of knowing that our guess is moderately correct. That's why this agreement, this exercise here. We calculate alpha, get alpha with our guess in here from experimental data, and see if they match. They don't match entirely, but they come really close, which means our estimate of how much energy is absorbed by one shell is not orders of magnitude off. Now that we guess this one or estimate this one correctly, we can now map the temperature of the shells. And we do this. This was done by Som, who's a current grad student. We do some FDTD imaging to do the electric field scattered on the surface, and we map the temperature. So here are thermal maps of the shell and the surrounding medium. So you can see that at the highest point here, the maximum temperature rise is about 40 or 35 degrees, which means the temperature at the surface of the shell is about 60 because this was being held at 25 degrees. So it's not heating it up anywhere close to hundreds of degrees. It's a very low rise that's causing enough for this thing to break. We can also plot the maximum temperature as superimpose on the wavelength absorption plot of the shells, and it kind of follows it really nicely. The better it absorbs, the more it heats up. So that was kind of nice. We have done some really interesting things with the shells too. Here we have captured bacteria. This is E. coli. That's the bacteria. Here's a shell that managed to capture one, and here's a shell that didn't. We've done more imaging, but I like showing this because you can see the bacteria that is inside, like desperately jiggling around within the shell. It's kind of cruel and interesting at the same time. It makes us happy to look at it. We are working on how to break the shell and bring the bacteria out. We can do that, but the bacteria are coming out dead for some reason. We have to break the shell and bring them out alive. So we are working on that part. We have also done some other work on nanoparticles and liquid crystal. Here we put quantum dots in a different liquid crystal, and they can arrange themselves into stripes, which we can heat, destroy, cool down, and bring it back, the little stripy samples. This is another one where we worked on using nanoparticles to create electric field to switch liquid crystal molecules' directions. This is like a light-induced display. Just like your displays work by applying a voltage and switching the direction, here we were switching it by using light. I don't talk about these two, but I have the papers and stuff you can look at. Yeah, that's pretty much the end. I'd like to end by thanking a lot of my students. Somebody is still, this is an old picture, as you can see. Matt is still here. I need a new picture. He's no longer in my group. I don't know where he went. Also, my other collaborators, the faculty who I have done a lot of work with, especially Casey, who's allowed us a lot of imaging at Stanford, and Jin, who's supplied us with interesting nanoparticles. And the funding people. This one is mostly NSF. So thank you for your attention. Yes.
How does it change from one liquid crystal to another?
Oh, it's a change of orientation. So I think it's, this is one type of liquid crystal. Some of them can change with pressure and other things too. So this one, as we increase the temperature, it just goes from, if it's disordered, we cool it down, it will give some sort of positional ordering. Orientational ordering. This is the nematic phase. So just by changing temperature, it can go from liquid crystalline to the fluid phase, to the liquid phase, and back, and so on. Yes, this liquid crystal that we use can have a smectic phase as well. Oh, we don't work with, so the smectic phase is very stable. It is very hard to destroy a smectic phase. So we've only stayed with the nematics phase, which you can think of as a soft phase because it's easy to work with. You can easily tip it over to the isotropic phase. This will work with the smectic phase as well, of course, yeah. But we don't work with the smectic. Smectic is like a crystal. It's no longer really a liquid crystalline phase. For displays and all, we also still use the nematic phase. Smectic is hard to mess around with. Even with electric field, it doesn't switch easy.
Do you have any control on the thickness of the shell?
That's a good question. We have some control over the size of the shell based on how quickly we do this cooling. So we go from isotropic to nematic. It's the same temperature change over which we cool it down when we are doing the shell formation, the one that was, here. If we cool very fast, if we quench the system, the shells are smaller and the diameters are thinner. So there is a correlation, but as of now, we have not been able to form a case where we can hold one and just change the other. So they both change at the same time. Yeah. And if we go slower, we can make bigger shells. Oh, the bubble in the bubble expansion? So you mean the one over here? Sorry, what am I looking at? Oh, the one outside. Uh-huh. Oh, okay, the shells, this one. It's so far it's been how quickly we cool the system when we are assembling them over here. So if we cool it, this process is taking seconds, and this gives us shells on the order of 1 to 3 microns in diameter. If we cool very slowly, we can make them as large as 10 microns. Of course, it would be a function of nanoparticle density as well. You have to have nanoparticles there. So what we think is happening is as you cool slower, it gives the liquid crystal more time for the nanoparticles to come close together into bigger aggregates. So this is, even the shells themselves, it's not the equilibrium. We are sort of, freezing the system here to form the shell. If we cooled it more slower, a couple of shells would have come together eventually to form a bigger shell. So that's what's determining the size. We can put this system in liquid nitrogen and take it out, and we get very, very small shells that we can barely see in a microscope. So we've worked with some theorists. We've kind of looked at, yes, in principle, I think it would. However, in practice, that would require a cooling rate that might be hard to control. Yeah, but in principle, they may not. I'm not sure if they would form a shell, though. They could just form a sheet, or I don't know about the geometry, but they could. They will eventually. They should all come together. Yeah. Well, these are, so the wall here, sorry, oh, it's just, I'm not sure why that's not happening here. When we form the shell wall, it is made up of multi-layers of nanoparticles. So it's not wow, this is not going to stop playing like ever. Okay, good. Sorry, I was just trying to get to this point. Over here, the shell wall does consist of many, many, many layers of nanoparticles already stacked. Usually we found that the diameter of the wall is about between 10 to 20% of the diameter. And that scales with the size of the shell. One of our collaborators has been doing this, and they have found a little bit lower than what we see experimentally, but about 10% or so. Yeah.